and welcome to the fourth chapter of image processing, which is two-dimensional discrete Fourier transform. So now this is what we are going to learn today in this chapter, which is introduction to images in the frequency domain, discrete Fourier transform, two-dimensional fast Fourier transform, image filtering, smoothing, sharpening, and homomorphic images. So now let's start with introduction. So now, as we know, image processing is the analysis and manipulation of a digitized image to improve its quality. So now, it can be done in both spatial as well as frequency domains. Now, the imaging operations can be done easily, very easily, in the spatial domain by manipulating your pixels. But the calculation can be done much more easily in the frequency domain. That is why transforms are used. Transforms are used to convert a particular image from spatial domain to frequency domain for ease of calculation and then convert it back to the frequency domain. For now, consider the example given over here. So case 1 and case 2. Case 1 has the number 12 plus 10 in Roman and case 2 has 15,000 plus 10,000 in long integers. So now these numbers can be converted to easier forms for calculation. The Roman numbers can become normal integers and the long integers can become 15 into 10 raised to 3 plus 10 into 10 raised to 3. So here the calculation becomes very simple as the format in which it is converted is very simple. So mathematical transforms such as Fourier transform and cosine transforms are used for this purpose. So now let's talk about images in the frequency domain. In the frequency domain, we don't analyze signals with respect to time. We analyze them with respect to frequency. What happens in spatial domain is that we deal with the images as it is. We receive an image and we process it as it is without making any changes. The value of the pixels in this frequency domain change with respect to the scene. So in frequency domain, what we do is we deal with the rate at which the pixel values are changing in the spatial domain. So now consider this flowchart given over here. The input image goes to the frequency distribution, then is processed, inverse transformation, and output image. So these two things over here are extra. Okay, so this is what is used to convert spatial images into frequency domains. So now these signals are converted from time domain to frequency domain using mathematical operators, and inverse transformation is to convert back to time domain. So they are done using mathematical operators called as transforms, which we did in the third or fourth semester in mathematics. The examples of these transforms are Fourier transform, Laplace transform, and Z transform, to name a few. So now let's start with Fourier transform. If you see these four images over here, the summation of all these four sinusoidal waves is this image, and the idea behind this was first thought by Fourier. So now Fourier transform is called as a frequency domain representation of the original signal. It refers to both the frequency domain representation and the mathematical operations that are associated to the frequency domain representation to a function of time. The Fourier transform is not limited to functions of time, but it is in order to have a unified language, in order to be common, the domain of the original function is commonly referred as a time domain. So now, as I said, once the image is converted to frequency domain, it has to be converted back to the time domain. So that is why we use inverse Fourier transform, which is also known as Fourier synthesis. The main applications of this is image analysis, image filtering, image reconstruction, and image compression. Now let's see what is discrete Fourier transform. Now discrete Fourier transform is the Fourier transform for finite length sequences. It can be used to exactly implement convolution for finite size arrays. So now this is the formula for DFT, and a periodized signal, periodic and sample transform is given with this formula. We use these formulas to calculate the DFT of a particular image. So now let's see the properties of DFT. So now these are the 10 properties of DFT. Just to name a few. There are many more properties of DFT, but these are the most commonly known and widely recognized properties, which is linearity, periodicity, discrete Fourier transform symmetry, discrete Fourier transform, phase shifting, separability, average value, Laplacian, rotation, distribution, and convolution and correlation. So now let's see what is two-dimensional fast Fourier transform. So now in discrete Fourier transform, the time taken to process an image or to transform an image is directly proportional to the square of the number of points that are present in the image. So for example, a transform on 1024 points using DFT takes about 100 times longer than the FFT, which is a lot of time. That is why FFT is done. What FFT does is that it basically does the same work but in a lot less time, but for that its requirements might be more and the quality might not be that great as compared to DFT, but it's somewhat similar. To perform FFT, the image which it has to be transformed so that the height and width are an integer power of 2, which means the height and width both should be an integer power of 2, which is 2 raised to 1, 2 raised to 2, 2 raised to 3, and so on. So now if you consider this image given over here, and this is the original image, and this image over here is the magnitude of the two-dimensional FFT, and this image has been transformed, and the width and the height of this image, the lower image, is an integer power of 2. So now Fourier transform, it decomposes an image into real and imaginary components, which is a representation of the image in the frequency domain. So now there are two formulas given over here. The formula on the left is used to calculate the fast Fourier transform of an image, and the formula on the right is used to calculate the inverse of that. Here f of m, n is the pixel at coordinates m, n. F of x, y is the value of the image in the frequency domain corresponding to the coordinates x and y, and m and n are the dimensions of the image. And the end result is equivalent to performing the 2D transform in the frequency space. So this is how you calculate the end result. And the formula on the right is used to calculate the inverse of it. The output of the Fourier transform is a complex number, and it has a much greater range than the image in the spatial domain. Now let's see what is the fast Fourier algorithm. So now, as I said earlier in the previous slide, that m and n are the dimensions of the image. So here, the dimension of the image is 1, then there is no problem. That means the image is very simple and it can be done in one step. So if the dimension is 1, then we just finish it. But if the dimension is not 1, then we go to step 2. For example, a function is given. So we break this function, we divide this function into two parts, which will be odd samples and even samples. Let x be the fast Fourier transform of even samples of u, and y be the fast Fourier transform of the odd samples of u. Then we construct the kernel D. Once we find out D, we multiply the kernel, which is D, with the fast Fourier transform of the odd sampled function, which is y. So your z becomes D into y. So then after that we find out the value of x plus z and x minus z. So now this is to get the value of f. Once this is calculated, we combine these two and get f. This is another concurring step. Then we return f and exit. So f will be used as your output. So now what this algorithm does is it involves a repeated division process for dividing the functions into odd and even functions, and computes the result and finally returns the solution by combining the results of the sublist. The sublist over here is x plus z and x minus z. This is known as successive doubling method. The complexity of this is big O of n into log of n, whereas the complexity of the discrete Fourier transform is big O of n square. And if you remember what you did in DSA or an algorithm analysis, big O of n log n is much lesser than big O of n square. So you can see that the complexity over here decreases and is much more faster. Now the remaining part of this chapter will be done in the next video. Thank you.